Hello and welcome to AP Statistics. This is lesson 1-1 through 1-3. We're gonna just try and do this on a video tonight. AP Stat starts a little slow, but it will pick up. Here we go. All right, as a little warm up, it says USA Today, and we'll reference real articles in this class. Some of them are a little old, but it works. It says reported both the number of manufacturing defects per vehicle and a satisfaction score for all brands sold in the United States. The data on number of defects are shown here. So this would be the number of defects per vehicle. So that's a lot of defects. Anyway, it's data. So apparently number of defects per vehicles, for brand. Okay, so this might be Ford. Ford had 76 defects, and maybe this is Mercedes, maybe this is Toyota, and you can see how that works out. It's hard to understand this data set, all right? Some good questions would be like, well, what's the most number of defects? What's the least number of defects? What's the average number of defects? So we could talk about all sorts of questions. Is 72 considered high, or is it considered low? I don't know. It's hard to tell. So what we could do is we could take these and put them in order. We could put them on a graph. We could appropriately display this data. And so how do you appropriately display the data? One thing to think about is what kind of data is it? So that's what we're going to go through in this lesson, is talk about types of data. So there's really three types of data. What kind of data is this? This is considered numerical because it's a number. Things like height, weight, number of defects, those would be numerical. You can give a number to them. Another thing with numerical data is that you can find an average. You can find an average of the number of defects. Another type of data is categorical. Categorical, you cannot find the average of. For example, the color of car. There's no such thing as an average color of car. But you could do like, how many red cars are there? How many black cars are there? Those would be categories. And then as far as numerical goes, if it has a number, there's continuous versus discrete. And we're going to get into this. This is just a warm up. Discrete means you can count it. You can count the number of defects. Continuous means you have to measure it. It's like you have to measure height. You have to measure weight. Anyway, we're going to get into that. This is just a warm-up. So there we go. What might you want to learn from these data? Which brand is best is what that says. If you can't read, my handwriting is not great. So you might want to learn which brand is best, which brand is worst. What's the average? What's the variability? This is a big word in this class. What's the spread of the data? All right, variability. How does one thing vary from the next thing? How can we represent the data graphically to show what you want to learn? Well, that's what we're going to learn in this lesson. Okay, here we go. When constructing a graph that will enable you to see the important features of data, choice of an appropriate graphical display will depend on these three things. The number of variables. This had one variable. It's a number of defects. And it's just, this one had 76, this one had 80, so you can see the number of defects is varying from company to company. The data type, which we'll learn about in this, and then the purpose of the graphical display. Okay, let's get into some vocabulary words. Variable, any characteristics whose value may change, or you could say the word vary, which is why we call it a variable. It varies from one thing to the next. From individual to another, one individual to another. Variables have variability, which is why, again, this word is huge in this class, variability. Political affiliation, it varies from person to person. That would be categorical. Maybe you're a Republican or you're a Democrat, you fit into a category. Number of textbooks purchased, that's numerical. And that's discrete because we can count the number of textbooks that are purchased. Distance from home to college. Now that's numerical, and that would be considered continuous because you have to measure the distance. Data. When I say data is the value for a variable from an individual observation. Data results in making observations either on a single variable or simultaneously on two or more variables. And then we got univariate, bivariate, multivariate. Univariate means single, because it's an observation of a single variable. Suppose a PE coach records the height of each student in his class. Each height would be a piece of data, and we can analyze the data. We can find the average height. We can find the interquartile range. We can do all sorts of standard deviation, which is all stuff we're going to learn in this class. Bivariate is pairs of data that work together. So numbers from two variables. For example, a PE coach records height and weight. And this is where we can get like a scatter plot. And I know you should know some of these. You've probably seen a scatter plot somewhere in the past. All right, so you record height and weight. And maybe there's a relationship between height and weight. Maybe as height increases, weight also tends to increase, which is probably what you're going to find on a graph. And then multivariate, we really don't do much of this in here, but if you want to go to university and study statistics, you can. Maybe we're looking at height, weight, and the number of sit-ups and the number of push-ups, for example. And maybe there's going to be some correlation between all of these variables for a person. Okay, two types of variables. We got categorical versus numerical. Categorical is also called qualitative. It's a quality, like a color or a shape, something like that. Qualitative. That says qualitative right there. I don't know why I put those both right there. It's a repeat. Consists of categorical responses. Which of the following would you say are categorical? Car model. That's a category. Birth year. Even though the year of birth is a number, it's a category. You fit into a category of the year you were born. You can't really take an average birth year. It wouldn't really make sense a lot of times. I mean, maybe you could think of a situation where it would make sense, but birth year would be a category. Type of cell phone, either Samsung or your iPhone, perhaps. You fit into a category. You can't really take an average type of cell phone. Zip code, even though it's a number, it's a category. You're categorized by your zip code. Which club you have joined. Again, you can join Japanese club, Spanish club, whatever club you want, but it's a category. Now, numerical, you will be able to find an average and it'll be meaningful for you. Another way of saying numerical is quantitative. And these words do get switched out. So even in your book, they'll say categorical, and in the next sentence they'll say qualitative. So you do have to associate categorical, qualitative, numerical with quantitative. Quantity, think quantity. Takes on numerical values. It makes sense to perform math operations on these. So if we can find average, we can find mean, median, that sort of thing. You can find the average of these. Which of the following is not numerical? GPAs, you can do average GPA. So that one is numerical. Heights, yes, you can do average height. So that one is numerical. Codes to a combination lock, that would not be numerical. I don't even know if that would be categorical. That would be a weird one. Number of text messages a day, yep, we can find the average number of text messages a day. Textbook weight, sure, we can do those. There are, now within the numerical realm, you separate those either into discrete or continuous. There are two types of qualitative variables, discrete and continuous. Discrete are isolated points on a number line, usually counts. You can count them. The number of cars in the parking lot, the number of students in the class, the number of students that passed the AP exam last year, which was actually really good. 91%. Anyway, number of textbooks purchased. You count them. Continuous, however, you have to typically measure. GPAs are measured. Heights are measured, weights are measured, times are measured. And it can take on any value. You can have a weight of exactly 50 kilograms. You can have a weight of exactly 50.000001 kilograms. You can take on any weight, you measure it. All right. Actually, what I would, if I was teaching you in person, I would have you go do example 1 and try to fill that out yourself. So pause the video, go do example 1, identify the type of the following variables. All right. And you're paused and you're back. Okay. Colors of cars, that's categorical. Number of calculators owned by students, that's numerical. And you can count the number of calculators, so that is discrete. Zip code, categorical. Even though it's a number, it's technically a category, and you do have to be careful about this situation. It's a little tricky. The amount of time it takes students to drive to school. We can measure the time with the clock, so that would be numerical continuous. And then this one, some people don't like this one. The appraised value of homes in your city. So perhaps, 200,050 cents. It's technically numerical because you can count the number of pennies that a house is worth. And it can't be, you can't have a fraction of a penny. Okay, so technically you can count the number of pennies that a house is worth. That's how our dollars and stuff works. All right, this is everything we will do this year. We'll cover all of this. Bar chart, dot plot, you already know some of these, probably histogram, scatter plot, and then you got your variable type, your data type, and then, yeah, we will cover all of this. This is just kind of an intro. You don't really need to know much about this. This is actually in your book on the last page, I believe. Oh, maybe not. It's somewhere in your book. It used to be on the back page. There it is, front page. See? Actually, that's a different thing. It's in your page. It's in your book somewhere. Don't worry too much about this. This is what we're going to go through. This is what we're going to learn. All right, now on to, I guess, 1.3. Let's talk about displaying categorical data. This is data that everything falls into category. Okay. So to comply with new standards from the U.S. Department of Transportation, helmets should reach the bottom of the motorcyclist's ear. The report motorcycle helmet 2005. We had 1,700 motorcyclists nationwide, and each time a motorcyclist passed by, the observer noted whether the rider was wearing no helmet, and you can see that in the chart here, non-compliant helmet or compliant helmet. So this is the good one. We like this one. We like compliant helmets. What we have here is called a frequency distribution. Frequency is the number of times that something occurs. So a no helmet occurred 731. Non-compliant helmet occurred that, and a compliant helmet occurred 816. Okay, so filling in the blanks here. Frequency distribution is a table that displays the possible categories along with the associated frequencies or relative frequencies. Frequency is a number of times that a category appears in the data set. How frequent does a variable occur? And then the relative frequency, so you will have to know this vocabulary word. Relative frequency is not necessarily the count, but the percentage. 731 no helmet people accounts for 43%. I should probably double check my math, but if I do 731 divided by 1,700, I should get 43%. Okay? Non-compliant helmets accounts for 9%, and compliant helmets account for 48%. Okay, so frequency is just the count. Relative frequency is the percentage. You're gonna have to know that. Now, if I add all these together, I get 100%. If I add all these together, I get 1,700. For a particular category is the proportion of observations. So you could say proportion there as well. Relative frequency, just like I did up here, is the frequency divided by the number of observations. So to get this 43% here, I took that number and divided by that number, and I got 43%. Now, here's what the bar charts look like for this. If you can see up here on this chart, the first thing was a bar chart. It's for one variable, and we use it for categorical data, and the purpose is to display data. So here's some bar charts. First thing you want to do when constructing this is draw a horizontal line and label. We have no helmet, non-compliant versus compliant. Second thing you want to do is draw your vertical line. Now, if you're doing a frequency bar chart, you put up the counts. So we need to count up to 816, which is why my chart here doesn't go up to 816. That's interesting. I don't know why this is not matching up. Anyway, that doesn't match up. That's embarrassing. It's weird. The data doesn't match up either. This must be from different data. Yikes. I guess I need to fix that, don't I? That's weird. Maybe I fixed that on your notes. These might be old notes. I think I did. I think I fixed that on your notes. Shoot. I did fix that on your notes. My notes are old notes. I'm sorry. Your notes are good. The notes that you have. I should have printed off your notes. But your notes, this should line up with this. But you can see here, what I want to show you here is that this is the frequency or the counts, and this is just the percentage. So on your notes, it's closer to like 63%. There we go. Problem solved. Next page. Jeez. All right, next thing we can do is basically put two bar charts together. We call them comparative bar charts. Comparative bar charts. This one, it looks like my data is good. Okay. So constructed using the same horizontal and vertical axes, usually color coded to indicate which bar group we use. Should use relative frequencies on vertical axes. You don't want to use the counts because the counts might be so far off that it would be hard to compare, but you can compare the proportions of the counts. Use relative frequency rather than frequency on vertical axis so that you can make meaningful comparisons. Okay, so here's an example. We have the students applying to college, and of parents, we have 12,715 high school students responded to the question, ideally, how far from home would you like the college you attend to be? So this was the students' response to the question, how far away from home? Less than 250 miles. Most of these students wanted to be less than 250 miles. And then look at the parents. The parents, most of the parents wanted their child to be less than 250 miles. More than 100 miles, I think this is supposed to say 1,000, by the way. Whoops. More than 1,000 miles. Yeah. So how does it compare? How does this number compare to this number? And then how does this number compare to this number? We can look in a bar chart. We can't really compare this number with this number. Like if you were statistically illiterate, you would say, wow, that's a lot bigger than that. But if you look proportionally, what's the proportion? This is about a third, and this is about half, okay? So you have to look proportionally. Why is the relative frequency bar chart more appropriate in this scenario? Relative frequency meaning the proportions. The number of students is far more than the number of parents, but proportionally, they might be similar. So here we go, here's the data. We have students versus parents. You can see it's color coded. This is your relative frequency. And we can compare. You got about 1/3 compared to about 50%. And then these actually end up being the same, roughly, even though in this right here, these are very much not the same, are they? This is very different from this. But you see that with the relative frequency. You don't see that with if we use frequency. So this one is bad. We don't want to use frequency. Because if you look here, look, this is way bigger than this. But if you look proportionally, they're about the same. So, rule of thumb here, comparative bar charts, when you're comparing two variables, you always want to use the proportion or the relative frequency. All right, example 4. So I would say pause, do example 4 on your own, read through it. And here we go, pause right now. And we're back. Okay, we have students at a local high school were asked which gaming system they preferred. PlayStation, yes, PlayStation 3 is an old question. Xbox 360 or neither. The graph shown at the right shows the results. Explain why the graph may be misleading. We had, this is percent. We had 49% say they prefer the PlayStation 3, and we had 46% say they preferred the Xbox 360. This is a 3% difference. Does this chart show a 3% difference? No, this chart shows that the PS3 is basically double, even maybe more than double. However, it's only 3%, it's 49 to 46. And the reason is, look where they started the graph. They started at 44.5%. So that is an issue. When you're displaying data, when you're displaying the relative frequencies or the proportion, you can't start here. You have to start at 0. You have to start at 0, or 0 in this case. This one was a bad one. You have to start at 0, or else things can start looking a little weird. All right, last page. Two-way tables. Sometimes data can show up in two-way tables. Here we have, we're looking at St. John's wort. Is it effective in treating moderately severe cases of depression? The study involved 338 patients. If you go over here, we have all of this data. And if you add up, so some people took St. John's wort, some people took Zoloft, some people took a placebo. Placebo is a new word. That is something that it doesn't have any active ingredients. It gives you baseline. And then some people had a full response, some people had a partial response, some people had no response. So we had 27 people that took St. John's wort had a full response to the drug. And apparently this is an 8-week period. And if you add this up, there are 91 total people that had a full response, 55 that had partial, and 192 that, if you add these up, you get 338. That's because we had 338 people in our survey. Now what you can do is you can take this data and you can find relative frequencies and plot them up. So let's find the relative frequencies for each. We got full, partial, none. To find the relative frequencies, for example, what proportion of subjects in the study were randomly assigned to take St. John's wort? That would be these people. 113. So if you take 113 and compare it to the total, that's about a third, 33%. A third of all participants took St. John's wort, and so forth and so on. And that's good. These are roughly about the same. And that makes sense because you have a third here, a third here, a third here. Maybe it would make more sense if they were exactly the same. Like if I was designing the study, I would probably have all of these be 113. So I don't know, whoever designed the study, I don't know why they did that. Anyway, let's go through and find all of our frequencies. So you have 8% there. How'd you get 8%? You take 27 divided by 338, you get your 8%. If you do that, now we have all of our frequencies, and now we can take this and go make our chart, we can actually make, you know, good diagrams, but I'm not going to go through all of that. All right, so what did we learn? Big things. We learned types of data. We learned numerical data versus categorical data. Within numerical, you have discrete versus continuous. Discrete can be counted, continuous has to be measured. We learned the difference between frequency and relative frequency. These numbers are different in your notes, so I apologize for that. We learned how to graph. If you graph frequency or relative frequency, you won't see a difference. However, if you're comparing two variables, you have to use the relative frequency or else you won't get any meaningful comparisons. We also learned that when you're doing relative frequency, you have to start at 0 or else you get something that's a little manipulative. Can you imagine people using statistics to manipulate the way you think? Imagine that. And then this is a two-way table. To graph it, you have to first convert to your frequencies. 8% of people had St. John's wort with a full response. And then you can compare you can compare these with these with these. And that's all I have to say about that.